Okay, guys, I'm really sorry I couldn't be there for this particular set of notes, but I do need to, but for time reasons, I want to make sure we get them in before the end of this week. So, we're going to start talking about how do we find the area, area when it comes to polar coordinates. And so, what I want to point out first of all is that now, because we're polar coordinates, our area is going to be similar to a sector, right? This subsection of a circle. So if this were a full circle, we would just do pi times r squared. And so, but it's not. It's this angle theta is a subsection of that circle. So so this is just a fraction of the circle, and if I wanted to think of, so we're essentially going to take that fraction of the circle times pi r squared. Well, a full circle is how many radians? And we would say 2 pi, right? So the fraction of the circle would be whatever theta is over 2 pi. Okay? And so with the real quick, we can say that the area of any given sector would be theta over 2 times r squared, because these pi's would cancel out. And r is going to be our function, because we write our polar functions as the radius in terms of whatever the angle is. Okay, and so essentially, if we want to do that and the way we're going to partition is, instead of doing rectangles that we're partitioning by like we would with rectangular coordinates, what we're going to do is we're going to partition by angles. So the area is going to end up being, so in general, it would be theta over 2 times the radius squared. But since we're partitioning by theta, it's going to be the sum of the angles between A and B of the function of theta squared d theta. And so the theta, and we would have a 1/2 in front. So the theta is equivalent to the sum of A to B of d theta. And then the radius of each of those things would be the function. So so let's kind of go through an example of what I might expect of you guys. So if we were to take out our calculators, I'm going to take mine out, but you won't be able to see it when I pull it up. If we were to take out our calculators and look at the function r equals 3 cosine theta, 3 cosine 3 theta, we would we'd see a graph that kind of looks a little bit like this, right? Where it went like this, and then like this, and then like this, and back around. Okay, we see that rose curve that we were talking about last week. So if we want to do one petal, what we want to be thinking about is what is essentially this area, or we could do this area. And so what we have to ask ourselves is, if we're only doing one petal, what do we know about the boundaries of the angles of those petals? Well, to get to the petal, to get one petal, the petals start with a radius of 0, and then they go out, and then they come back to have a radius of 0. So essentially, we want to find for what values of theta make this radius 0. Okay? And so what we're going to do is to do 3 cosine 3 theta equals 0. Now, we could just say, like, start thinking through, we have this area model, right? So we can say the area is going to equal the 1/2 times the integral. We have that the radius is 3 cosine 3 theta, the quantity squared d theta. And the problem is we don't have the bounds. And so the solving of this equation will help us determine what are the bounds of one petal. Okay? So let's see. First I'll divide that 3 out front out, and so what we get is 3 theta has to equal 0. And so that means what we have to decide is, well, what are the values of cosine that make the function equal to 0? And we would get pi over 2, and then 3 pi over 2, and then 5 pi over 2, and you get the basic idea here. And that's what the angle needs to be. So if I go ahead and divide all of those by 3, because the angle inside our cosine is 3 theta, not theta. Okay, we get theta equals pi over 2 over 3 is pi over 6. 3 pi over 2 over 3 is pi over 2. 5 pi over 6. And so if you watched your calculator as it did this, it started here. It actually started here and went here. And so it gave us, so from 0 to what ended up being that first one, pi over 6, 0 to pi over 6 is what gave me half of that first pedal. And then if I want to keep going to get a full pedal, I could do from pi over 6, keep going, and then back up to pi over 2. So I'm going to use pi over 6 to pi over 2 as my bounds. Now, some of you might be thinking, well, couldn't we have just started here, and then we could have done, for instance, negative pi over 6 to positive pi over 6, and that would be fine. Or you could have said, oh, I'm going to do, well, here's pi over 2. I'm going to do from pi over 2 to 5 pi over 6. That would be fine. All of these would be fine. It doesn't matter as long as your bounds are appropriate here. And again, it's worth noting that each time our area is like tiny wedges being added together instead of rectangular areas. And then once we do that, once you've set up the integral, to find the area, just type in your calculator. I'm doing so right now off screen that you guys can't see. Making sure you're putting your parentheses in all the right place and all that kind of stuff for the integration function, d theta. And, guys, I got, oh, I typed this in wrong. I can tell that I typed it in wrong. And y'all, I got that my area equaled 2.356. So hopefully you guys are getting the same thing here. So let's look at some other examples. Okay, so let's go ahead and look at this next one where we have r equals 1 minus 2 sine theta. I'm going to give you guys a second. Go ahead and type that in your calculator so you can get a feel for what this looks like. And hopefully you have a graph that looks kind of like mine. And we can certainly see there's an outer loop and an inner loop. Okay, and so if we were to start this from 0, my first section of this would be essentially here. And hopefully you notice that I'm kind of like starting and wedging out, like almost like little radiuses out to the curve here. Okay, so just the area of that section would be from 0 to what? Well, to find that what, we would want to figure out, well, where is this radius equal to 0? And so some real quick of that, I can see that if I real quick solve that for sine, I've got that the sine of theta equals 1/2. And we know that that happens at pi over 6 and 5 pi over 6. So this little blue section here that's nice and easy, that is essentially from 0 to 5 pi over 6. And then, so just the area of that piece would be 1/2 times 0 to pi over 6 of 1 minus 2 sine theta, the quantity squared d theta. But then what happens here is if I keep going, I have this red area, right, which is not the area I want to find. And then I'm going to keep going again. So I'm going to skip over that red area because that's not the area I want to find. So to that little blue area, I'm now going to add a new purple area. We'll call this one the purple area. And that one would, so we're going to add into that 1/2. And that one goes from 5 pi over 6. I'm sorry. I screwed up this bound earlier. This bound should have just been pi over 6. Sorry, guys. So, but this next one starts from 5 pi over 6 all the way to essentially pi. But then when I try to get in the rest of this area, oh, we got to finish this out. 1 minus 2 sine theta squared d theta. When I try to add in this green area, okay, I would do 1/2. That green area would go from pi to 2 pi. Okay, but I have to take that red area away because it's not, because that green area goes all the way to the origin and we're not including that. Well, that red area was defined as pi over 6 to 5 pi over 6. And if you're like me, you're finding this to be a really, really icky approach. However, it would work. Now, what I might choose to do is start my graph, start my shading a little bit differently, and I might say my area is going to go from here, and I'm going to rotate around here to here. So that would be the area from 5 pi over 6 to 13 pi over 6 because I've gotten a full rotation. And then subtract my inner area. And this is just like a different way of thinking about it. You're still going to have to do outer area minus inner area. It's just how you got to be thinking about your functions polarly instead of thinking about them linearly, right? So outer and inner has a whole different vibe because the outer and the inner happen at different angles of theta. So it's not like you have one circle outside another circle. It just feels a little bit different. To find the answers to these, I'm going to go ahead and throw this in my calculator. Oh, and I kind of screwed up. Each of these would have a 1/2 in front. So for the first one, I got 8.881, and then from that, I'm going to subtract 1.63. And I found that the area is equal to 7.25. That seems like quite enough for today. I will give you guys the next example tomorrow.